All right, let's get started again. So in the previous video, I introduced the concept of scaling. And what we have shown is generally referred to as classical scaling scheme. Okay. And because of various limitations, the classical scaling scheme could not be implemented fully. Okay. And because of that, there are variations such as constant field scaling or generalized scaling and so on. So there are many different variations that are used in the industry. But the idea of this course is not really go into the details of it. So I'll quickly tell you what are the limitations of classical, one of the limitations of classical scaling, and how that comes from some physical principles. We can analyze that. Okay. So I said that we have to reduce the lateral and vertical dimensions by factor alpha, and also increase the doping concentrations and reduce the supply voltages. Well, to reduce supply voltages was one of the problem. This was a graph that we have seen already in the last video. And in that, we have focused on the blue curve, which is capturing the technology node over the last 40, 50 years. But I've also plotted here the supply voltage. Okay. So what you see is that, let's say if you look at 1980s, it was about 12 volts. And then it came down to about 5 volts, and then to 3.3 volts. And then after that, it's been continuously reducing. The reason why you don't see a gradual change in the supply voltage is that our digital chips have to interact with the environment which is surrounding us. It is not working in isolation, right? So let's say if your cell phone charger has some chips in it, and the converter will have a certain output voltage, let's say 3.3 volts. It has to work at that particular voltage, because if you change the voltages at every node, then all the peripheral circuits that are used with your digital chips also have to change, which is not a very cost-effective thing to do. That is why in the 80s and 90s, the voltages were not scaled along with the sizes, but they were kept constant for some time and then scaled down. So this gave rise to what is known as constant field scaling, or rather constant voltage scaling here. So for two generations or two nodes, the voltages were constant and then came down. So this is sort of only the qualitative picture. And what you'll also notice is that over the last 10 years, there has not been much change in the voltage, because that voltage was stuck at around 1 to 1.1 volts or so. And I have not really given you the voltages in the latest generations, because this data is not really that easy to parse. And from various sources, I have put together these numbers. So these are qualitatively the picture what happened over the last 40 years. Okay. So why this sort of trend in the voltage? Okay. We can understand easily the argument that peripheral circuits will have to, the digital chip has to interface with the peripheral circuits, and so the voltage has to remain constant. That was fine. But in the recent years, the reasons why the voltage is not scaling is actually something to do with the fundamental device. So you might have seen this graph already, right? Wherein we talked about the drain current and the gate voltage. And we have plotted the drain current in the log scale and the gate voltage in the x-axis. One of the features of digital circuits, when we introduced the various device metrics, we said that ion to I-off ratio is an important metric. So if you look at this picture here, x-axis, this is 1.8 volts. So this is 180 nanometer CMOS technology. Okay. So the channel length and width are quite large. And the VDS for this graph was 1.8, and VDD is also 1.8, of course. Okay. So you get this curve. This is actually the real data that you would reproduce in an experiment if you fabricate this using 180 nanometer technology. So in this case, the ion is basically here, wherein let's say it's about let's say ion to I-off is what we are interested in. And ion is basically 10 power minus 4, let's take it approximately. And I-off is when gate voltage is 0, let's take it as 10 power minus 10. Okay. So this ratio is about 6 orders of magnitude difference. Okay. 6 orders of magnitude. And we said when we are introducing the device metrics that digital circuits would prefer to have as high ion to I-off ratio. That means when the device is on, we want large current to flow, and when the device is off, we want as small current as possible to flow, so that this ratio is very high. Then it is an efficient digital circuit. Otherwise, if the off current is large, let's say off current was 100 microns or, or 10 microamps. Okay. If the off current was somewhere here, let's assume, okay, let's say instead of this, the device was performing like this, something like this. Okay. This is second device. Let's just, is it a good digital device? Well, it is not, because you see the I-on to I-off is only 2 orders of magnitude, and it is no good, because even when you switch off the MOSFET, a lot of current is flowing through it. That means the batteries are getting discharged, or there's a lot of power dissipation, which we don't like. Okay, so we want high I-on to I-off ratio. So now, how is that related to the supply voltage? Well, supply voltage is generally the largest voltage that you have in a MOSFET. So in this technology, it is 1.8 volts. I mean, you can always have some flexibility in adjusting that, but not a whole lot. This is the nominal voltage, we can call it. Okay. So now in this technology, what is the threshold voltage here? So you could say, you could try to plot, let's say take this, extrapolate this. Let's say I'll have this, and in this direction I'll extrapolate, and I'll say it is somewhere around this. This is my VT. Okay. Remember, when I say on, above this, the MOSFET is on, and below this, the MOSFET is off. Okay. So this corresponds to a logic 1, and this corresponds to a logic 0. And we want, sufficient margins so that the logic 1 and logic 0 are not mixed up, because we are building chips with billions of transistors, and finally it's all voltages. Maybe one transistor will have a 0.8 voltage, other transistor might have 0.85, other one might have 0.675 or something like that. So when you have various voltages, we want to have good margin so that the device operation is not incorrect. Because if you have any circuit that computes the value incorrectly, then there's no use of having a computer. We need that reliability. So we make sure that there is sufficient margin. So because of that, let's say for this latest generation technologies in the last 10 years, VDD has been roughly about 1 volt, approximately. Okay, sometimes it might be 1.1, 0.9. Yeah, each foundry will have a different number, but roughly about 1 volt. The reason for that is, if say the threshold voltage is 0.4 or 0.45, so you can think of the higher side. Let's say if your 0 is my ideal logic, this is my 0 volts, it is my logic 0, and 1 volt is my logic 1, right? So now in between I have my VT, which is, let's say, around 0.45 volts. So I want, what prevents me from reducing my supply voltage? After all, I can build a battery with 0.6 volts. Okay, so what prevents me from having that? The reason is that if I reduce this, if I, let's say, put my supply voltage here 0.6, if I do this, VDD equal to, let's say, 0.6 volts. If I do this, then the margin I have for the high, logic high, right? In this case, in the previous case, when it was 1 volt, I could say this is my logic, this is margin or noise margin high, I'll call it NM high, NMH, noise margin high, and this is my noise margin low. So my low will be about 0.4 noise margin, and the high side I have 0.55 or so. I have sufficiently large margin. So even if the 1 is not truly 1, instead of 1, it might be 0.8 or 0.7 as well, still it will be considered as logic high. Okay. But the moment if I reduce my VDD to, let's say, 0.6, then my noise margin high will become only 0.2. Sorry. This will become a noise margin high will be equal to 0.2 volts. That means instead of VDD 0.6, what if that the voltage for some reason, because of some interference or because of some sudden change in currents, there's a spike, and then we saw the voltage drop down to 0.3. Then it will be interpreted as logic low, and we don't like that because that leads to an error in the computation, right? So for a good device reliable operation, we need to have high noise margins. Okay. So now you might ask, well, I mean, why can't I reduce my VT? Okay, I can't completely reduce. So let me say I'll keep my VDD as 0.6 and I'll reduce my VT to 0.3. Okay, so why can't I have that? Let's say 0, 0.6, and let's say VT is 0.3. So I have 300 millivolts of noise margin high and 300 millivolts of noise margin low. Why can't we have this? Well, The reason for this, this is also difficult to achieve. It's not that it's impossible, but we pay a price. And what is the price? The price is something to do with the sub-threshold swing that we talked about. We can't arbitrarily reduce the threshold voltage because remember what we discussed about sub-threshold swing. Sub-threshold swing. Okay. We said for a classical MOSFET, where you have current flow because of electrons jumping over a barrier, this is about 60 to 90 millivolts per decade. Okay, that means if I have, let's say, 1 microamp of current, okay, how much gate voltage should I have to reduce it to 1 nanoamp in a classical MOSFET? Let's say I start with, I'm just taking an example. Let's say ion is 1 microamp, and my I off, I'll say I'll live with, or rather, I want to have 4 orders of magnitude change in the current. Okay, so I'll live with I off of 100 picoamps. Okay, this is what I can have. 4 orders, only 4 orders, not 6 orders. 4 orders I'm asking. Okay, if I want 4 orders of magnitude change in the current, how much gate voltage should be different? Now, how much should get? How much reduction or reduction or decrease? Decrease in VG is necessary for 4 orders of magnitude, right? What you would need is effectively, let's assume 0.75 or 75 millivolts as an average subthreshold slope, okay, which is a realistic thing. Generally the devices nowadays have 75 to 90 millivolts per decade. Okay, so let's take it as 75 millivolts per decade. And how many decades? 4 decades, 4 orders, right? So I will need at least 0.3 volts. Okay, if I don't have 0.3 volts, I can't switch off my device. So that's why if you want to reduce, let's say, make VT of 0.2 volts, 200 millivolts VT, I can in principle think of VT of 200 millivolts, but if I use that in a CMOS circuit, my off current is going to be large. Let's say, because if I want to plot this in this graph, let me erase this part of it, and say, if I want to have VT of, let's say, 0.2 volts, then I might have to fabricate a device which is like this. That means my I on to I off ratio, right? Not this is actually still high. Well, if I have this, let me, yeah, the current might follow something like this. So there is no significant I on to I off ratio. Okay, that's why we cannot scale the supply voltages. Reducing VT implies I on to I off reduces, which we don't like. This is one of the limits, and because of that, the threshold, the supply voltages have been stuck at 1 volt. So what, you might ask? Well, we saw that the power dissipation in a chip is going to be proportional to CV square times frequency. Okay, capacitance times voltage square times frequency. Voltage square, if I reduce my supply voltage, I can reduce my power dissipation and still increase my frequency. Okay. So I can try to make my device operate faster, but it turns out that it is a difficult challenge. This is a very multi-dimensional problem that requires some of the best brains in the world to address, and that's been happening for the last 40 years. But there are a lot of challenges, is what I wanted to tell you about. Okay. So anyway, so this is basically the fixed voltage scaling. And it turned out that over the years, there were many other challenges. And nowadays we change each parameter by a different amount. So we call it generalized scaling. And we can analyze what happens in each of these scenarios, but it is not necessary for the purposes of this course. What I wanted to show you now is basically to convey the finer impact of this. We understand the basic principle from the classical scaling scheme, and we understand one of the limitations. Let's say even the doping density maybe could not scale it. Okay? There are so many other limitations. We'll forget all that part. Okay? We understand at least at an intellectual level what is the requirement. So with all that, this is the result. This is to me a very, very impressive slide, because this data here shows you how the various parameters of a microprocessor have behaved over the last 50 years. Okay, so this was originally collected by Horowitz and others, and finally, recently, I've taken this data from GitHub, from the website of this guy Carl Rupp. So he has collected this, and then he keeps updating it, every now and then. So this is the data up to 2019, I think. Okay, so what you're seeing on the y-axis is a logarithmic scale. Okay, on the x-axis you have the years. The first thing you notice is the number of transistors on a chip, okay, on a microprocessor, and it has been increasing exponentially over the last 50 years because it's a logarithm, so it's going to be a straight line. So exponential increase in the number of transistors. Why? Because we said that every 2 years or so we are doubling the number of transistors, and because of that you get this sort of a behavior. Okay, great. So why large number of transistors? If you have larger number of transistors, you can implement more logic operations. Okay. Now you might have studied in your basic electronics course how to build a counter or an AND gate or so on, right? You might not have studied how to build them from MOSFETs, but finally they're all built out of MOSFETs. And let's say if you have a NAND gate, you need 4 transistors, 2 input NAND gate. Or a NOR gate might have again four MOSFETs and so on. So if you are able to have more transistors, you can build more logic circuits. That means your computers are more versatile. Microprocessor is more versatile and more powerful. Okay, you can have a larger bit processor. Initially we had 16 bit, then 32 bit, then now 64 bit, and so on, right? So you are able to have that because you are able to build in more transistors, and because of that, the processing capability is increasing. Okay, that is one of the features we have noticed. The other graph you see in green is the frequency of the processor. And you see that initially there was a gradual increase, and it is logical because we saw that as you are scaling by about reduce the sizes by 0.7 or scale it by 0.7, we saw that the frequency was increasing by about 40% each scaling, right? Each scale down. So this was what happened over the till 2000 or so. But after 2000, it sort of saturated in a range of few gigahertz. The reason this happened is because finally frequency is set by how fast you are able to charge and discharge capacitances in your circuit. Okay, so it turned out that this RC delays became a problem. It was not possible to discharge the capacitors as quickly as we want. Ideally, we want to do it instantaneously, but if you do that, the current limitations of the technology doesn't permit it. So we are not able to go beyond this frequency. We can do it at a single transistor level, sure. But then once you integrate, let's say, 1000 transistors, it's very, very difficult to achieve very, very high fast switching speeds, especially with silicon. Okay, there are other alternatives, but silicon, yeah, it is not that easy to increase the frequency more than this few gigahertz. Okay. So what is the solution? This is an industry that never stops, right? It is there is a very famous saying of Gordon Moore that no exponential is forever, but forever can be delayed. Okay. So now what happened was, since the frequency was saturating, what the industry did was they came up with a clever idea of introducing more number of cores. So till 2000, mid 2000s, you would never have seen a multi-core processor. But nowadays, everybody has a multi-core processor. Your cell phone has probably 8 cores or 16 cores in it, right? Why? The reason is individual core is not able to do, you're not able to scale the frequency of individual cores, but I can always parallelize it. I can distribute my computing job on more cores, and I can make the overall system more efficient. And that's why over the last 15 years, we see that the number of logical cores have increased in the processor. Okay. Fine. And the last thing, I want you to know is basically the power. In our scheme, classical scaling scheme, we saw that we are able to reduce the sizes by 30% and maintain the same power, right? Because the power dissipation was, or rather, I said 50% reduction in the power. So you can keep the same power and double the number of transistors, right? So, we wish that was true, but it turns out that practically there are many challenges in achieving it. And so what was realistically possible was this. You see that initially there is good number of, power was increasing because we are increasing the number of transistors. But then after some time, we are not able to increase the capacity more. The reason is if you have more power dissipation, you're heating up your silicon. Once you heat up silicon, we know all bad things will happen. Mobility can reduce, and threshold voltages can shift. Whatever transistors or circuits you have designed so carefully, they might not work as you want them. So we don't like them to be heated. Okay, that's why you'll see that most of the times computers are kept in, especially servers are kept in air-conditioned rooms, because if you don't have good temperature control, then they might not work correctly. Okay, they'll have many glitches and their lifetime will reduce. So that's why even intrinsic, the power dissipation in a CMOS chip is very important parameter, and we sort of we don't want it to be higher than about 100 watts. This I think is this is roughly about 100 watts, 125, 150 watts maybe. Okay, so this is 122, 120 watts, let's say approximate average. We don't want it to be much higher than that, because if you have much higher, then you have to cool it. You have to already we have servers which have water cooling and things like that. You need much more aggressive cooling techniques to make sure that there are no problems in the technology. Okay, but whatever it is, overall it definitely is an impressive technological achievement. Perhaps the greatest technological achievement in the last 100 years. The reason is, I know many of our Indian kids are very interested in software, right? You can do a lot of software only when you have hardware. If you don't have the hardware, you can't really do anything. So this is the technology that has really given you this sort of a hardware to run whatever programs we want, and whatever we talk of artificial intelligence and everything, right? They've been there for a long time, but people could not implement them because the computation capacities were limited. But now we have these huge systems which can actually enable artificial intelligence or machine learning and things like that. All of that, the heart of it is all semiconductor evolution that has happened over the last 50 years. Okay, so I just wanted to give you a few glimpses of what this is about. This is not the technical part of it, but I think it's important for us to understand and appreciate what the technology is about. Okay, this is a slide which I have taken from a presentation by Mark Bohr at Intel in 2017. He gave a presentation on continuum Moore's law, and in that he shows how the processor areas have reduced. So this is 45 nanometers, that means this was about, I would say about 2007. To this is 10 nanometers, would be about 2017 maybe, right? 18, 17, 18, or even 16 maybe. Okay, so about 10 years, the area has shrunk. Each time the area has shrunk like this. So initially what started out as 100 millimeter square area of a processor now is about 7.6 millimeters. So roughly, less than, more than 10 times shrink in terms of, the area, overall area. Okay. So the reason this has been possible is because of the scaling that we have described. We are able to increase the transistor density, but simultaneously it turns out that the process complexity has increased. What I mean by process complexity is that the semiconductor chips have to go through a manufacturing process, and it's not easy to fabricate. This is done in a very high-end fab, and you have thousands of steps that have to be executed so that we have the chips, right? Semiconductor chips. So this is not a semiconductor fabrication process, and that will be dealt in a technology-related course. Well, as a technology-related course, but essentially the message is that the process complexity has increased. So that is what is captured in the bottom figures here. So this is evolution from last 10 years or so. You see that the area per transistor has reduced. This is a log scale, so exponentially reduced area per transistor. And process cost also has increased exponentially. Okay? Because we are always, if you want to go from, let's say, 45 to 32 nanometers, we have to invent a lot of tools, a lot of material processing, equipment, everything has to be invented and developed so that we achieve this, right? So a lot of cost is gone. The state of the art semiconductor fabs are now, upwards of $5 billion, $8 billion or so, if you want to establish the state of art. It's so expensive. But the good thing is, because finally the cost is going to be a product of this too. So what you get is the cost per transistor, which has been exponentially reducing over the last 10 years. The cost per transistor has reduced, and we are also selling the devices by millions and millions of cell phones and all. So some of the cost is getting recovered. Of course, semiconductor industry is always profitable because there is this exponential growth in the demand. Okay. So the cost per transistor has reduced, which has enabled us to have more and more powerful machines in our phones, right? The supercomputer of the early days is now, probably much worse than your cell phone. The ordinary cell phone, which is probably even 5,000 rupees. That's probably much more powerful than the supercomputers of 60 years back. Okay. So yeah, this is how the economics of the industry worked. And we have, because you can always have beautiful technologies, but if it's not economically viable, it is not going to become useful. So it's been economically viable technology, and that's why we have this revolution. And I just wanted to close with a couple of images, which I find them very, fascinating. It's very easy to talk about the, nanometers and nodes and all that, but finally, what is this? How small is a MOSFET? Okay, the traditional MOSFETs are micron size. How small is today's MOSFET, right? And I'm not even showing right now the images of the latest MOSFET. This is still 10 years back, in the lecture after next. So I'll show you some images of the latest MOSFETs. But before that, this is 32 nanometers technology, which is about 10 years back. And in a particular technology, the size is what we always brag about. All the semiconductor industries brag about the size, right? Because there is something called a static random access memory, which is SRAM, which is part of every computer. And to build an SRAM cell, you need 6 transistors. So if you build 6 transistors together, we make one SRAM cell. And how much is the area of that cell? That is a very important thing. Okay? This is the simplest circuit, and companies always brag about this. Even if you look at IDM presentations of Intel, you will see the SRAM cell areas. The reason is that is very comparable. That tells you how good your technology is. So this is static random access memory of 32 nanometer technology, and you see that the area of this is only about 0.17 micrometer square. It's not very, illustrative when I say 0.17 micrometer square. So what? Well, the size of this 0.17 micrometer square is this compared to this white area, which is actually the red blood cell of a human body. So when you have a cut, you see blood flowing out. It has lots of red blood cells, and you can't even see them. You put it under a microscope and you see a red blood cell. This is going to be the size relative to the SRAM, which is maybe 1,000 times smaller than that. So, and this has 6 transistors. Okay, if you have an SRAM, like a body, human RBC of a body, probably you could build 1,000 SRAM cells in this. 1 kilobyte of memory you can build probably, or even 10 kilobytes. I don't know. Okay, you can pack all these SRAM cells together and build a memory array. So that will be the size of your memory. That's why you're able to have SRAMs, DRAMs, which are gigabytes now, right? DRAM sticks which are having 64 gigabytes and all that. That is because we are able to pack more and more transistors. Okay, and this is the scale we are talking about. I sort of like this image that captures, how small, how advanced the technology is right now. Okay, and the other image is again, this is a comparison, the same SRAM, but compared to the SRAM about 40 years back or 30 years back. In 80, the SRAM cell size was about 1700 micrometer square. By 2010, it became 0.17. So in 30 years, the size has reduced by 10,000 times. Whatever is today's SRAM cell would be much smaller than the contact. In this, you will probably not understand what all these things mean here. So these are all some connections and some contacts. You see here, these bright spots are the contacts. Okay, so your SRAM cell is probably going to be very, very small compared to the contact of 30 years back. That is the extent of technology that's been, that's advanced. Okay, so yeah, with that, I would like to stop my discussion on the scaling part of it. I hope you understand what scaling means and what technology means. If you open a newspaper sometimes, or you check online, what Samsung is producing, or TSMC is producing, or Intel is producing, they'll talk about 5 nanometer technology, 3 nanometer technology, research and all that, right? So you might understand what they're talking about. So I would ask you to just check out those things. It's interesting. This is one of the forefronts of technology, and always, it is very, very exciting to keep up with that. Okay. With that, I'll stop this discussion. In the next lecture, I'll describe scaled MOSFETs. Okay, so we understand now what scaling means, what it looks like, and all that. What is the current characteristic of a scaled MOSFET? I'll discuss that in the next lecture. Okay, and finally, I'll discuss some things called as short channel effects. Maybe the discussion will go to half an hour to 45 minutes. After that, the last lecture in the MOSFET series will be the latest MOSFETs. Okay, all right. I'll see you in the next videos. Thank you very much for your interest. Take care.